Okay, you wanted more? Let's do a little more. So the next thing that we want to talk about is what's called an unconformity. And so there are three types that I want you to be able to identify. And these are something that we can see in the rock record. They also give us some information about the sequence of events that have occurred. So that's really what our goal is for relative age dating, is what happened here. So we can put rocks in order, but of course we'll come to find out in future modules that looking at the rocks themselves can tell us the environment that existed. So not only can I tell you that rock layer A came before rock layer B, but I could tell you that rock layer A might have been a beach environment, and then rock layer C was a offshore environment like a coral reef or something like that. And so that'll just be some more information. But the unconformities, you have to remember that we are depositing material typically where there is a low-lying area, because sedimentary rocks are making up a huge portion of the sequence of rocks that we see. Think of like the Grand Canyon. And so what we see is that near coastal environments is where we get the biggest sequence of deposition, which means we're recording most of the material there. But where's that material coming from? It's actually being weathered or eroded off, right? So it's stripped off of high areas. And so in those areas, there is existing rock there. That rock tells us a story, but it is being destroyed. It is being removed. And the removal of that material is sometimes what we would call an unconformity. It is a place where there is something missing. And so when we see two rocks that are in contact with each other, they're touching each other, we can assume that there's some missing time there. And so there's a couple reasons why that might be. One of the big ones is erosion, that there was a stoppage in deposition. We're no longer adding layers, but we're actually taking away layers. And so when I see that contact, I can say, wow, there was a layer deposited and a layer deposited, and then something changed. So we have to think that low-lying areas do not stay low forever. Plate tectonics tells us that. Collisions of plates are causing the surface of the earth to rise, and then erosion is stripping them down low. And so areas are constantly going, and we say that in a big geologic timescale thing, from high elevations to low elevations, and high elevations and low elevations. Think about the Grand Canyon. If you've ever been there, when you stand on the top of the rim, on the south rim, and look into the gorge, you are standing on a limestone, and there are shells in there that you can see, fossil shells, that only occur under the ocean. But you are standing at 7,000 feet. So how did we get those fossils to be at 7,000 feet above sea level? Well, we could argue that sea level may have been 7,000 feet higher and had deposited those, and that's how they got there, and then has dropped. But there's no real evidence to support that sea level could get that high, even if we melted all of the ice caps. So the other explanation is that the land surface has actually been uplifted. And that is what we think is happening in a lot of places, is we have low areas, deposition, 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 layer, 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 formed into rock, and then uplifted and sometimes stripped away. In the example here, the contact, or what we're calling an unconformity, is easily visible because of the orientation of the layers. One at the bottom is almost near vertical, and the one at the top is relatively flat. And so it would still argue that the one on the bottom is older, but this unconformity, this line that I've drawn in yellow, tells us something else. There was an erosional event. And also remember, we said that sedimentary rocks should be deposited flat, so if they're tilted, it tells us that there's something occurring here. And that's probably a collision which caused the rocks to be uplifted. We had to then strip all those rocks down low, flat, so that then we could take more material and wash it in and start piling up again. So some of these unconformities can represent a significant amount of time. Sometimes it's hard to see in the field, but when these big time differences occur, millions, sometimes even billions of years of missing time, we could argue that there has been a huge event here. So the three types we want you to be able to identify. One is what's called a disconformity. And the way we're going to tell the difference is really rock type and orientation. And so in this case, we're going to say that a disconformity is between two sedimentary layers that are parallel to each other. So just because there's uplift doesn't mean our rocks have to tilt. They do a lot of times, but not always. And so we would argue that the land surface where we're at is low. We have mountains, hundreds of miles away that are washing in material. And so I'm building up layer upon layer upon layer of rock or sediment that eventually turns to rock. But then something changed. A boundary has been altered or something has changed that causes these rocks to now uplift. So they rise up, but they stay relatively flat. No more deposition because I'm not the lowest area. And so I start stripping some of these rock materials away. And then as I strip them away, they become low again, and I can now deposit more material on there. And so usually fossils are needed to be able to tell that there is an erosional surface or a missing time gap there. So we could see that in the canyon in a couple places where we have two said rocks on top of each other, but they're horizontal, they're parallel to each other. That's the key here. That is what we would call a disconformity when they're parallel to each other. Okay? The next one still involves sedimentary rocks, but now here's the key. They are not parallel to each other. And so this is this idea that there's been some event that has uplifted the rocks, causing them to no longer be flat. They're horizontal, they're tilted. Erosion comes along, strips them away, and so now they're low again, but the rocks, below the Earth's surface are now tilted, and then we can deposit flat-lying rocks on top of that. And so it's really about the orientation here. Okay, so flat rocks on tilted rocks, that's an angular unconformity because they're at an angle to each other. And so hopefully this little diagram would help. So what do we see here? Low. We're at low elevation here. We're near sea level. Somewhere off to the right, there's a bunch of mountains. We're weathering those. Pieces are breaking apart. They're being washed down here, and they're deposited layer upon layer upon layer. As they get buried, they turn into rocks. But over time, what happens is we have something change here. Maybe a plate boundary off to the left becomes a new boundary. We have a collision, and we've crunched the rocks here. So they've been bent. In this case, they've uplifted and been tilted. And so I can't deposit here anymore because it's a highland, right? So now all the material is washing away from here. So I'm taking the material off of this area and I'm stripping it down. And so as I strip it down, I remove material. I'm not recording. I don't know what's happening here. All I can say is that there has been an erosional event or something that stopped deposition here. And then once we erode, weather, we become low again, and now I have the opportunity to deposit more material here. And so then if we come along and there's a little road cut like right here, I have said rocks and said rocks, but they're at an angle to each other. This contact here is the unconformity, and it tells me that there has been a stoppage in deposition. It could be from uplift and erosion. That's a typical way we get these unconformities. It could be that no deposition occurs for a period of time, right? So that could be another explanation for why we have a stoppage in deposition. But here the key, of course, is the angle of the layers across the contact here. I don't care if this whole block was tilted 45 degrees on an angle. This would still be an angular unconformity here where they touch. I don't care about the overall angle of even the unconformity can be tilted. Don't care. You want to look at the unconformity and say, what are the relationship between the rocks below and above? If they're flat, it is a disconformity. Even if this whole block was tilted and the rocks below were flat and the rocks above were flat, that's still a disconformity because we're comparing above and below the erosional event or the unconformity. If they're at an angle to each other, boom, they're an angular unconformity. And then a nonconformity is the last one, and this is rock type. So we're not looking at relationships between orientations. We're saying, look, if you have a metamorphic rock on the bottom, or a plutonic igneous, not volcanic, right? The rocks that cooled, crystallized inside the earth. If you have those on the bottom and said rocks on the top, it's a nonconformity no matter what. And why is that true, right? The argument is that both those rock types, plutonic igneous and metamorphic rocks, form deep inside the earth. Sedimentary rocks, how do we get those? We weather surface stuff, and the material washes down and lays on the surface of the earth and then slowly builds up. Well, I can't have pieces of rock land on a plutonic igneous or metamorphic because they form miles inside the earth. The only way to get a sedimentary rock that's depositional touching one of those rock types is I have to strip off all the material that's covering that plutonic igneous rock or metamorphic rock and bring it to the surface. Then I can take my pieces and deposit them directly on top. So because those are in a depositional contact, said rocks on top of those two, it has to be an unconformity. And so if you can identify the type, boom, you know it's a nonconformity. Okay, so what does all this mean? Well, we like to give you puzzles like this. And so here is a puzzle that you could be given, and it would ask you to put these things in order. So I'm going to suggest, and I should have done this at the beginning of the first video, I'll probably put it in the module, but after you go through the lecture material, I would suggest that you do the homework first before taking the lecture quiz. Practice, because there's some questions and things about unconformities and puzzles to make sure you understand it, and then go ahead and take the lecture quiz. Because if you can do the homework, you can do the lecture quiz, no problem. But let's take a quick peek at this. So what we would say here is that this layer D is an igneous rock, and so is layer H. All these others are sedimentary rock, and it doesn't really matter what this is because we're going to use the cross-cutting relationship, but it could be another igneous rock. So what you'd want to do is put this in order from oldest to youngest. You would have to look and say, okay, F is cutting across all of these layers, so they have to be there in order to be cut. So I know that when I have said rocks, oldest is on the bottom. So I would start with A, and then B came along, and then C. I have to be careful with this layer here. I drew on some red lines because they weren't on the original image to tell you that there is a baked zone here. And look, there's also inclusions. There's a piece of E in D. I can't get that piece there unless E is already there. Same with the bake zone. I can't bake E unless it's already there. So I have to go A, B, C, E. And then somewhere off of this diagram, molten rock started to come up from deep in the earth, found a weakness between these two layers, C and E, and oozed its way in between here. It melted some of this stuff, and it incorporated a few pieces, and it baked them. So A, B, C, E. Then D, and of course F cuts everything there, so then I can cut them. It doesn't cut G, which means G wasn't there. But look, this contact right here where G is an unconformity. It is mostly an angular unconformity. Said rock, across that boundary, they're at an angle to each other, so that is an angular unconformity. Technically, right here where an igneous rock is on the bottom, and this would be a nonconformity. So we can have multiple depending on the rock types. But still, let's go back to our order. A, B, C, E. Then D oozes in. Then F cuts across. Then there's some uplift. How do I know that? The layers are tilted, and there's a unconformity. So although the rocks aren't telling me that, the missing stuff is telling me that an uplift event happened. Then erosion stripped off a bunch of material. How much? I don't know. Maybe there's stuff that I will never know because erosion and weathering removed it all. But then it became low again. I deposited G. Then I'm going to go H, I, J, and K. Why did H just come in a nice little stacked order? Because it was a volcanic rock, which we treat like sedimentary rocks. The other clue, only a bake zone on the bottom. that tells me it flowed across G and baked it, but I did not exist. So it didn't ooze in between anything. It just flowed along the surface. There was nothing above it. After it cooled and crystallized, we stacked those rocks on top. And voila. And then, of course, you can get complicated ones like this. And so I'm going to go through a quick sequence really fast, but you can do this in the PowerPoint. You can see that you have intrusive rocks, rocks cutting across, tilted layers, flat layers, even an erosional canyon. And we can jump through a sequence like this where we have deposition of layers here. So they get stacked up. Lutgrid, I don't know what that name is. On the bottom, it's the oldest. And then we go younger as we stack up. Then there's some intrusion of some molten rock that cuts across some layers here. Then there's a tilting and uplift event here that strips off some of the material, even down to the granite that once was buried deep in the earth. Then we start depositing some flat layers because we're low again. Even other material was probably deposited above this thing, but I don't know what that is, because after this dike that came across here that cut through everything, there was another erosional event, even though the rocks weren't tilted a second time, and stripped off this material. There could have been 5 layers here. Don't know what they were. They're gone. At this location, they're missing. Now, if I go laterally to, the east, west, north, south, I might find some evidence of those layers, and that can help me piece together what happened during that missing time. But right here, don't know. So another erosional event that brings it flat, which then means I can stack more stuff because I'm low again. So I stack a bunch of stuff, and then I have a river come along and it carves a canyon, and voila, we get this lovely canyon that we see here. All right, so this is what we'd expect you to be able to do. Now this one's a little crazy, and even this last one that I want you to practice on is a little complicated, but if you adhere to the rules, right? So superposition, old on the bottom, cross-cutting relationships, bake zones. These are the keys to helping you put things together, right? So if you'll go through this here, I'll put the answer to what this is and why, but I want you to try this one out, because this is kind of the things that we'd ask you to see or do in either the lab, because we're doing conformities in lab really quickly, I think next week. And then we also, of course, on the quiz and the homework, I'm going to have you put some puzzles together. So just stick to the rules, and you should be able to figure out the order of the relative age of these rock units.